Unit 3C, Lesson 3. In this lesson, we're going to discuss exponentials and logarithms. We're going to start by determining how to write an exponential in logarithmic form and vice versa. Then we're going to use those ideas to help us solve exponential equations and logarithmic equations. There are many properties we can use when it comes to logarithms. There's the product rule, quotient rule, power rule, change of base formula, and then the equality rule. We'll get to these other ones later on, but for the sake of this lesson, we're just going to focus on the power rule, which tells us if we have a log with base a of x raised to the p power, we can take that exponent p and bring it down as a coefficient. Okay, so all we're doing, taking that exponent, bringing it down as a coefficient, making it easier for us to work with some equations. So an example of the power rule, if we had log base 3 of 4 raised to the x power, we could bring that exponent, which is our variable x, down as a coefficient. So now we would have x times log base 3 of 4. This is useful in trying to solve for x because now we could just divide by log base 3 of 4, which is going to be some decimal, so that we could isolate x by itself. Next, we're going to go through how to rewrite a logarithm in exponential form or vice versa. And the reason this is going to work is because if we have a logarithm and an exponential with the same base, those are inverses, so there's properties that relate them. So if we have log base b of x equal to y, and we have b to the y equal to x, notice that the base of our logarithm and the base of our exponential are the same. The value we're equal to in our logarithm becomes our exponent in our exponential. The value in our logarithm we start with is going to become the value we're equal to in our exponential. Another way that might help you remember how to rewrite from one form to the other is that since we know these are inverses, we know the domain of one of the functions is going to be equal to the range of the other function. And another way we can think about that is input and output. So if we have our input for our logarithm, that is going to become the output for its inverse function. So if this is our input for our logarithm, becomes our output. Same with our exponential to logarithm. If our input is y in this case, that is going to become the output in the equivalent logarithmic form. Now we're going to go through a couple of examples rewriting in the other form. So first we're going to start with a logarithm. We have log base 7 of x equal to 2. So the base of our logarithm becomes the base of our exponential. Our output is going to become the input for the exponential. And then the input value, which is x, is going to become the output value over in our exponential. So we get 7 squared equal to x. Now we want to rewrite the exponential in logarithmic form. So the base of our exponential is 2. So we know we have log base 2. Our output is 32. So that is going to become our input in our logarithm. So we know this value is going to be 32 equal to our input in this case was x. So that's going to become the output of our logarithm. So we end up with log base 2 of 32 equal to x. That is the general process for how to rewrite a logarithm in exponential form or an exponential into logarithmic form. Now we're going to use the idea of rewriting in the other form to solve a few problems. So we have log base 3 of the quantity x minus 8 equal to 3. So first we're going to rewrite this in exponential form to make it easier to work with. Remember that the base of our logarithm is going to be equal to the base of our exponential. Our output of the logarithm is going to become the input of our exponential, and our input of the logarithm is going to become the output of the exponential. So now we get 3 cubed equal to x minus 8. 3 cubed is 27. To get x by itself, we would add 8 to the other side. So 27 plus 8, we get x is equal to 35. So to solve this logarithm, it was easier to write it as an exponential and then isolate x by itself. In this problem, we have log base 2 of the quantity x plus 8 equal to negative 3. So just like the last problem, we're going to write this in exponential form and then try to isolate x by itself. So rewriting this in exponential form, we get 2 to the negative 3 power equal to x plus 8. Now we need to simplify to get x by itself. 2 to the negative 3 is the same as 1 over 2 cubed. We always want to work with a positive exponent. We would subtract 8 to the other side to get x by itself. Now 1 over 2 cubed is 1/8 minus 8 equal to x. So you could write this as a mixed number or as an improper fraction. 1/8 minus 8 is going to be negative 7 and 7/8, which if you wrote that as an improper fraction would be 8 times 7 is 56. 56 plus 7, that would be negative 63 over 8. So just like the last problem, we first rewrote this in exponential form and then isolated to get x by itself. The next problem we have, if e raised to the 9.5x power is equal to 3 and the natural log of 3 is equal to 1.0986, we want to find the value of x. ln refers to the natural log. It's just a common logarithm that we use, so it has a special notation. L of n, the natural log, is the same as a log with base e. Okay, so whenever you see ln, the natural log, think of a logarithm with base e. Now to solve for x, we're going to take our exponential and rewrite this in logarithmic form. So the base of our exponential is e, so the base of our logarithm will be e as well. Our output is going to become our input, and our input of our exponential is going to become the output of the logarithm. So this will be equal to 9.5 times x. Now this is where we have to remember that log base e is the same as ln, the natural log, because we know what the natural log of 3 is. So since the log base e is the same as the natural log, we can rewrite this as the natural log of 3 equal to 9.5x. Now we can substitute 1.0986 in for the natural log of 3. Now we have 1.0986 equal to 9.5x. The last thing we would have to do is divide by 9.5. And if we do that, we get x is approximately 0.we'll go to 4 decimal places, 1156. So in this problem, we started with an exponential, rewrote it in logarithmic form. We have to recall that a log with base e is the same as the natural log, so that's why we could substitute 1.0986 in for the natural log of 3. We were given that information. Then last step, divide by 9.5 to get our approximation for x. To end this lesson, we're going to do a few different story problems. The first story problem, a certain radioactive material decays according to the law A equals A sub naught times e raised to the negative 0.021 t power, where A sub naught is the initial amount present and A is the amount present in t years. What is the half-life of this material? Round the answer to 2 decimal places. So since we're dealing with radioactive decay and half-life, we don't necessarily need to know the initial amount and the ending amount. We just need to know the relationship that this is dealing with half-life. So if we let the initial amount be equal to 1, the half-life, how much is present, is going to be half of that. So half of 1 is 0.5. The reason we would do that is because now we're just taking 1 times this expression, which is just going to give us that expression. 1 times anything is itself. Now we have 0.5 equal to e to the negative 0.021 t. The problem is that we have our variable in the exponent. So now we're going to use that power rule we talked about at the beginning of the lesson. But before we can use that, we have to take a log to each side of the equation. The log we want to use is going to have the same base as our exponential, so we want to use a log with base e, which is going to be the natural log. Now if we take the natural log of each side, we have the natural log of 0.5 equal to the natural log of e raised to the negative 0.021 t. Now we apply the power rule. We bring our exponent down as a coefficient. So we have the natural log of 0.5 equal to negative 0.021 times t times the natural log of e. The natural log of e is just going to be a value of 1 because we have log base e of e. So that essentially, since those are inverses, going to cancel out, leaving us with the value of 1. 1 times anything is itself. So now the last thing we need to do is divide by negative 0.021. You would just plug this into your calculators. The natural log button is going to be towards the bottom left side if you have a TI-84. And if you plug that in, you get t is approximately 33.01. So the correct answer in this case would be C, 33.01 years. That's how long it would take this certain material, radioactive material, to get to its half-life. Now we're going to get to our last example for this lesson. The number of bacteria present in a culture after t minutes is given as B equals 10 times e raised to the kt power. If there are 3,527 bacteria present after 3 minutes, find the value of k. Plugging in the information we know, we get an equation 3,527 equal to 10 times e raised to the 3k power. Now we just want to solve to get k isolated by itself. The first step would be to divide both sides of the equation by 10. Now we have 352.7 equal to e raised to the 3k power. Just like we did in the last problem, the value we're looking for is in our exponents. We need to bring that down as a coefficient using the power rule. So we have to take the natural log of each side of the equation. So after we do that, we have the natural log of 352.7 equal to, when we take the natural log, our exponent comes down as a coefficient. So we have 3k times the natural log of e, which we talked about in the last problem, is just a value of 1. Now to get k isolated by itself, we would just have to divide both sides by 3. And when you do that, you get k to be approximately 1.955, which just represents some constant for this certain type of bacteria culture. We talked about a lot in this lesson. Main ideas: be able to rewrite an exponential into logarithmic form or a logarithm into exponential form using the ideas of the relationship of inverses, inputs, and outputs. Then use those properties to rewrite exponentials or logarithms in the other form to make it easier to solve problems.